In this topic, we will see the application of double integral. Basically, we will explore the physical applications like computing mass, electric charge, center of mass, and moment of inertia. But I will explain more about the mass and center of mass. So in order to find the mass given a density function, but like that density is a continuous function on the region D. For example, if we have this region D, and we have just one rectangle which represents the xy. So this is the density function, density xy equals to limit of changing the mass divided by changing area. So this is changing the mass and this is changing area. So this changing area is the area of the small rectangle that contain the xy coordinate. Then if you have more rectangle of the same size, then we can find the total mass m. So we will end up getting good approximation for the mass, because then in order to find the mass will be the limit when k goes to infinity and when l goes to infinity, summation of I equals to start from 1 to k, summation of j equals to 1 to l, then our function of density, then changing area. So this limit is exactly the same as we can approximate the mass. So when we have more rectangle region, then we have good approximation for our mass. So we can change this one to a mass to find the mass as double integral of our density function by dA. So this is the formula that we are going to use to find the mass. So mass equals to the double integral of density function with respect to this region D or this region D. The other one is how to find the moment and center of mass. In this case, in order to find the moment and center of mass, we are considering a lamina with a variable density. So now in this case, the density is not constant. That is, we have a variable density. So the moment of entire lamina about the x-axis is given by the formula this, and if it is about the y-axis, is given by this formula. So like all the formula are the same. When it is mass, it's just the double integral of density. When it is momentum of the entire lamina about the x-axis, we multiply the density by y. If it is momentum of entire lamina about the y-axis is, we multiply the density by x. Then in order to find the center of mass, we divide the moment of the entire lamina about the y-axis divided by the mass. It gives us our x coordinate. Then to find the y coordinate, it will be moment of the entire lamina about the x-axis divided by the mass. Then basically we will find the center of mass. So the physical significance is that the lamina behave as if its entire mass is concentrated specifically at certain region. So if you have we have this region, maybe the center of mass is here. So it's like the mass is concentrated specifically at this point, which is x prime, y prime. To make it more clear, we will see two examples. So the first example is, let's say, find the mass and center of mass. The region D is given by as a triangular region with a vertex 0, 0, vertices 0, 0 to 1, 0, 3, and we have a density function x plus y. So the first thing is, since we need to find the bound for the x and the y, we have to draw the triangle using this vertex given, the vertex given. So basically this line is y equals to half x and this line will be from the 0, 3 to 2, 1 will be y equals to minus 3 plus x, or it will be 3 minus x. Looking this region, we can say this is as a type 1 region or a type 2 region, but let's choose our region as a type 1. So the bound for x will be from x is equal to 0, x is equal to 0 to x is equal to 2, and our y bound will be the lower line to the upper line. So this is our bound. So to find the mass, we will use this formula. So a double integral of the density function dA by d. So we already have the bound. So we say our equation like this. So integration of x plus y. So first we integrate with respect to y. Then our y bound is from half x to 3 minus x. And our x bound is from x equal to 0 and x equals to 2. Then we apply our knowledge of integral. Then we end up getting the mass equals to 6. So we already get the mass. So now we're looking to find the center of mass. So in order to find the center of mass, first we have to know the moment of the entire lamina about the x-axis and about the y-axis. So to find mx, we multiply our density function by y, and the bonds are the same that we found from our region, our triangular region. So it will be x y plus y squared dy by dx. So first we have to integrate with respect to y, then we will integrate with respect to x. Then we apply all the concept of the integral that we have, and we will get mx equals to 9. Then in order to find my, the moment of the entire lamina about the y-axis, we multiply the density function by x, and we keep the same bound. Then it will be x squared plus xy dy by dx. So we integrate first with respect to y, then with respect to x, then we find 9 over 2. So hence we have the mass, which is equal to 6. Then in order to find our center of mass, it will be my divided by the mass, then mx divided by the mass. Then we already get our my to be 9 over 2, and we know that the mass is 6 and mx is 9 over 6. Then when we simplify, we will get the center of mass, which is 3,4,32. So basically, the total mass of the region is concentrated at this point. The second example I have is a lamina occupy the part of the disk given by x squared plus y squared less than or equals to 4. Then it is in the first quadrant. Find the center of mass if the density at any point is proportional to the square of its distance from the origin. So, in order to find the mass and the center of mass, we need to know our density function. Then the density function is not given, but like it's say if the density at any point is proportional to the square of its distance from the origin, so we can find our density function. We know that the density formula is this one, which is x minus x1 plus y minus y1. Then we know that it is the distances from the origin. So we know that our x1 and y1s are 0, 0. Then we can say the distance is square root of x minus 0 squared plus y minus 0 squared. Then we already know that it is the distance is, it's say, to the square of its distance. So we can square the distance, so there's no more the square root here. So our density function will be kx squared plus y squared. Then we will we can either use the xy coordinate or the polar coordinate, but I will prefer to use the polar coordinate since we use xy coordinate in our first example. So from the polar coordinate, we know that our r square is x squared plus y squared. So from here, we can substitute in place of x squared plus y squared here, we can say it is equals to r squared. So our density function in terms of r and theta will be kr squared. So the second step is we have to find our bound, the bound for our r and the bound for our theta. Then from the equation given x squared plus y squared less than or equals to 4, we can, it's basically, it is a circle, then we know that the radius is 2. So since it's saying that it is in the first quadrant, so we only focus on this part, this region of the circle. So our radius is from 0 to 2, then our theta will be this angle, so it's from 0 to pi over 2. So in order to find the mass, we know that the mass is double integral of the density function by dA. Since we are working on the polar coordinate, dA means r dr d theta, then our density function in terms of the r theta is kr squared. So we just substitute. We know that the bound for r is 0 to 2, and for theta is 0 to pi over 2. So we can say the bound, then using the knowledge of integral, we will end up getting 2 pi k. This is our mass. We already get the mass, which was the first question, and the second question is find the center of mass. In order to find the center of mass, first we have to find the moment of the entire lamina about the x-axis and about the y-axis. So to find about the x-axis, we will multiply the density function by y. But since we are working on the polar coordinate, instead of y, we are using r sine theta. So we use the same bound and we use the same function for density, which is kr squared. Just what we are going to do is multiplying r sine theta with our density function. Then we will end up getting kr sine theta r squared r dr d theta. Then applying the concept of integral, and we will get 32 over 5k. Then in order to find my, we multiply the density by x. But now we are working on the polar coordinate, so we have to say instead of x, we have to say r cosine theta, because every expression should be in terms of r and theta. Then it will be kr cos theta r squared r dr d theta. Then apply the concept of integral, and we get my to be 32 divided by 5k. Then we know that our center of mass, we know that x is my divided by the mass, and y is mx divided by the mass. So my is 32 over 5k, and we know that the mass is 2 pi k, so it will be 1 over 2 pi k. Then we found our x prime to be 16 over 5 pi, and our y prime be 16 divided by 5 pi. So we get our center of mass 16 over 5 pi and 16 over 5 pi. So we get the mass and we get the center of mass. Also, if you want, just for practice, you can work on the xy coordinate or the Cartesian coordinate using the x and the y. So basically, the density function is kx squared plus y squared, and we know that the equation for the disk is given by x squared plus y squared less than or equals to 4. So write the expression for a y. So y will be plus or minus root 4 minus x squared. So since it is in the first quadrant, we know that both our x and the y is positive. So everything starts from 0. So we ignore the negative part. So our x bound be 0 to 2 and our bound will be 0 to root 4 minus x squared. Then using the formula, you can do it and you can end up getting the same answer. You can practice.